In this video, we will study about a very powerful clustering algorithm called DBSCAN. We will see what are the advantages of using DBSCAN and what are the disadvantages of using it. And finally, we will also see a brief demo of how to use DBSCAN present in the scikit-learn library in Python. So let's begin. So DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. And it was initially given by Ester and Sander in 1996. And then they came up with a new paper in 2017 where they revisited DBSCAN. So DBSCAN is a density-based clustering algorithm. And here, given a set of points in some space, it will try to group the points that are closely packed together. So there are mainly three inputs to it. Obviously, you will need to enter the data points to work with. And then these are the two main inputs. One is epsilon. So it's the radius of neighborhood with respect to some points. So if these are the points in a space, these are the points, then if we are considering this point, then we can widget all the points that are within epsilon distance from this point. This is called epsilon neighborhood of this point. So it can be in any direction. Maximum epsilon, it can be less. So it's easy to draw a circle with radius epsilon in all the direction with respect to this point, taking this point as the center. So if some point is here, then this distance will be less than epsilon because distance from this point till here is epsilon. And this, so any point falling in this circle will be in the neighborhood of that point. So this is one condition. And then we have min points. So if we have a point and we have, let's say, 1, 2, 3 points and this point itself, so its neighborhood will have 4 points within epsilon distance. So this min points parameter says that if a point has more than min points within its epsilon neighborhood, then that point will be called a core point. So we will see more definitions here. So we can divide the points into core points, border points, and noise. So in the same example, if we see this, let's say min points is 3 and epsilon is 1 unit. Let's say it's equal to this distance. So if we see epsilon neighborhood of this point, we see that there is only one point in this neighborhood. So this is a noise. Now, if we see this, let's say we have more points. If we see this point and we draw it, let's assume this distance is 1 or epsilon. Then we see that it has 1, 2, 3, 4, and this point itself. So here number of points is 5, which is more than min points. In our case, min points was 3. So this point will be a core point. Now if we see for this, it will be this circle 3. So again, this is a core point. Similarly, this, if this is connected, but this is, let's say, connected to this only, then this is not a core point, but it's connected to a core point. So we will call it border point. And border points are also part of the same cluster. If it's connected to any core point, then it's also included. But here it's not connected to a border point or a core point. So we will call it noise or outlier. So this algorithm is very robust to noise also. It will be more clear when we see this algorithm working on a real example. So first, let's understand what is directly reachable point. So if we have a point P and we have a point Q, then Q is directly reachable from P if its if P has to be a core point. So it's not that this is a cluster. Some points are here within this cluster, and this is a border point. So we included in this cluster, and then here is again another point, which is also a border point. It's not possible. So a point which is connected to just a border point is not a border point. So border points are points on the border, and it cannot be used to extend the cluster. So if this is a border point, and this point is just connected to this border point, so it will not be part of the cluster. It will be noise or maybe some other cluster. But let's say if this point was a core point, and this point is just connected to this core point, then this point will become border point and it will be included in this cluster. But it cannot further extend the cluster. So the directly reachable is also related to this. So P has to be a core point. Then Q will be directly reachable if it's within epsilon distance. So this D has to be less than epsilon. If Q is beyond epsilon, then it will not be directly reachable from P. So points are only said to be directly reachable from core points, not border points. Now another term is reachable. So this was directly reachable and this is reachable. So reachable means Q is reachable from P. So let's say P is here and Q is here, and there are many points between them. Let's say this point is P1, which is equal to P, and last point is Pn, which is equal to Q. And intermediate points are P1, P2, P3, and so on, Pn minus 1. Then the first point is P, second point is Q. Then we will see that Q is reachable from P. You should be careful that we are not saying directly reachable. Directly reachable is only core point, and this point is directly reachable from P. But here there can be many points between P and Q, but the condition is that all has to be directly reachable. So P1 has to be directly reachable from P0, P2 has to be directly reachable from P1, P3 has to be directly reachable from P2, and similarly Pn has to be directly reachable from Pn minus 1. And we had seen that a point is directly reachable from only a core point. So here in this case, P has to be a core point. P1 has to be a core point because P2 is directly reachable from P1. So this is also core point, this is also core point, core point, core point. But this Q can be a core point or it cannot be a core point. For example, in this case, Q was not a core point. So only exception is that the last point may or may not be a core point. All the other has to be core point and connected. That is, the distance between P and P1 is less than epsilon. Similarly here. So P1 is P, Pn is Q, and Pi plus 1 is directly reachable from Pi. So all points are core point except the last. Last can be a core point, may not be a core point. So let's move further. And let's do this on this. Let's understand the core points and other points on this example. So we will start randomly with some point, and here we have taken this epsilon, this length. So let's say we start with this point. We will label core points with red, border with blue, and noise with black. So we come to this point. We draw a circle of this radius. We see there is no point, so we can straight away make it noise. Let's say next we visit this point. These are part of a set, so we can traverse any non-visited node. So let's say we start here. Then we see its neighbors. So one neighbor is this. We see that it's connected because it's less than epsilon. Similarly, this is also connected. This is also connected. And this, let's say this is also connected. So its 4 neighbors are connected to it, and one is this point itself. So here connectivity for this point is 5, or density is 5, and here requirement is 4, so it's more than that. So clearly this point is a core point, so we color it red. Now straight away we can say that these are also part of this same cluster, because these are connected to a core point, so these are at least a border point. These may be even core points, because we have not explored all the neighbors of these neighbors. So we will not label it border, but we will move to one of its neighbors. First we look at all the neighbors, and then we expand one of the neighbors. So we come here, it already has one connectivity, so we see that this is connected to it, and this is also connected. So it has 3 neighbors and one this point itself, so total becomes 4. So this is also a core point. Now we will expand one of its neighbors, let's say this one, and it's not connected to this point, just this. So its density is just 2, this point and this point. So we will label it with border point, and this is a core point. Now we come back to this parent node, and here we came from here, so we go back here, and its next neighbor is this. Its connectivity is also 4, so it's a core point. Similarly, this is a core point, but this is not a core point because this is connected to this, only this and this, so it's a border point. Similarly, this is a border point because it is connected to a core point. Now we move to next unvisited node, let's say here. Again, this is not connected to any point, so it's a noise. Next unvisited is this, and this is also a noise, so this will be the cluster. So this is one cluster, and 2 and 2, 3 points are noises. Whereas if we had done some k-means, and let's say we had taken 2 clusters, then it would have divided into 2 clusters, and the centroid would be somewhere here for this and here for this, and these would be in one cluster, these would be in another cluster. Now let's understand the DBSCAN algorithm. We have just seen that in this example, but let's understand this formally. So first we compute the neighbors of each point and identify core points. Then join neighboring core points into clusters. So all the core points, if they are neighbor, these are part of the cluster. And then for non-core points, we will be left with non-core points. Some of them will be borders, some of them will be noise. So for each such point which are not core point, we will try to add these points to a nearby core point. So maybe this is a core point near to it, but it's more than epsilon distance. So then it will automatically become a noise. But if some point is within epsilon distance of a core point, then we will assign it border point and include it in the cluster. So for each non-core point, we will either make it a border point or otherwise noise. So let's see this another example and it will be clear. So let's say we start from here. We see that it's connected to this, this and this. Here min points is again 4. So its core point, similarly, this is a core point, this is a core point. Similarly, this and this, but this is not a core point because it's connected to this and possibly this, so it's less than 4. So this is a border point, and similarly this is a border point because it's connected to this and this, so density is 3, and this is connected to more than 3, so we will mark it as core point. Now we have visited this connected component, so we will pick another non-visited node from the set. Let's say we go here and it's not connected to any other point, so it's noise. Similarly, this is noise. This is possibly connected to this, so we should have visited this in this connected component itself. Then this is a noise, and now this is a core. It's connected to this, and this, and this one is also a core point. Now this is a border point. It's connected to a core point. Similarly, this and this. And the others are noise. So you see that we have identified two clusters here. This is one cluster and this is the second one. If you had used some other algorithm like k-means, then and given two clusters, then possibly it may have clustered these into one and the others into second, and the centroid would be somewhere here and here. So it would not have detected the outliers or the noise, whereas in the case of this algorithm, it has clearly identified the outliers. So it has found two of these clusters which look correct if you had done it manually also. So that's why it's good compared to other algorithms. So let's see some of the advantages of DBSCAN. So first is that we don't need to specify the number of clusters. It automatically figured out these two clusters. Then it can find arbitrarily shaped clusters. So it was pretty arbitrary, and even you can have clusters like this. Points are in a circle and some points are in the center. So this algorithm will figure out that these outer points are one cluster and these inner points are other clusters, provided you have given good epsilon and num points. So if you pick epsilon very large, then these all will be within the epsilon neighborhood and this will be one cluster. If you have given epsilon too small, then it will be too many clusters. And if you do epsilon correctly, then you will see that this is one cluster and these outer points are second cluster. And these are robust to outliers. So we had seen here that it was able to detect the noise. And mostly insensitive to ordering of points in the database. Some exceptions are that some border points, let's say this border point is connected to this core point also and this core point also, and these are in separate clusters. These core points are not connected, but this border point is in proximity of this and this. So it may either go to this cluster or this cluster depending on the order in which we pick the points. Otherwise, mostly it's insensitive to the order in which we pick it. Now let's see some of the disadvantages. So this needs some understanding of data in order to choose a proper epsilon and min points, and it may require some experimentation also. And it's not entirely deterministic. It's due to the same reason that this border point may get to this cluster or this cluster depending on the order we pick, but that's not a big deal. And it doesn't work well on clusters having large difference in densities. So if a data set has, let's say, two clusters, we can clearly see that. But we see that in the first case, it's very dense and these points are very close to each other. And in the second cluster, these are a bit apart. So it's difficult to pick one epsilon which will work for both of these. If we pick very large epsilon, then it may grouped into one cluster. If we pick very small epsilon, then this may be in one cluster, but these may get clustered into many different clusters. So here, picking a suitable epsilon may be tricky. Now let's see this in our running code in the notebook, and it will be more clear. So I will be using scikit-learn's DBSCAN library. So first let's import We will be using the double moon dataset that is very popular, and it's like this: one moon and one other moon. So there are some points along this and some points along this. So we will be using this in our example. And I also like to avoid warnings in these notebooks, so I will just ignore the warnings. You may skip these lines, these are optional. These are generally long warnings and it becomes irritating sometimes. So let's run it. And now we will load the data. So write a comment here. Let's pick 200 points and let's add some noise. We will see what is the effect of adding noise, what happens if we don't add noise. And let's print first 5 elements of this. So you see that it's an array of 2D points, and this level will contain 0 and 1. So this data set, double moon data set, has 2 clusters. So either the level will be 0 or 1. So you can print level. In fact, you can print the complete level. You see that it's 0, 1. But we will not be using it because we will be using clustering and it's unsupervised. We can just plot this to see the actual plot, the correct clustering, and then we can plot our own clustering, whether it was clustered correctly or not. Now we will train the model. So first load the model. And we will pick epsilon of 0.25 and min samples, which is same as the min PTS which we had seen in the algorithm. And then we will fit the model on X. Let's run it. And now let's print models level. So this is the cluster generated by our model, level generated by our model. And this is the original, the correct level. So it seems it has also identified 2 clusters, which looks quite similar to this one. In fact, it looks exactly similar to this one. We will plot it and see how well it has figured out the clusters. All the X points, all the Y points, first column, second column, and then we need to specify C. So otherwise all the points will be labeled in same color. So here we will just pass the model dot labels. So if it has 3 levels, then it will be plotted in three colors. In this case, it looks like it has just 2 levels. And then let's plot it. So you see that it has correctly classified these. Let's also plot the labels. Here we had passed model labels, the trained model. We will also pass just the label that we had read from the data set. This label. And let's plot it. So we see that both look exactly similar. So let's add some more noise and let's run it again. This should differ because it will every time create new points. So here you can see the difference. With more noise, we can see the original level will be just 2, but here this has found 5 clusters. So we see that now it's not that correct, but it has created 4 clusters. Let's try one more time with, let's say, 0 noise. So with 0 noise, it will be exactly this. So there will be no problem in clustering these. Let's try adding some smaller noise, 0.1, 2, and run it. So we see that it does a pretty good job. So these all points are clustered into one cluster. These all are the second cluster, and you can see 2 noisy points here. So this and this are noise, because possibly these are just connected to a border points and none of the core points. And here also you can see these noise as -1. So 2 -1, and in the plot you can see these 2 points. So this is a brief demo of how you can use the sklearn's DBSCAN library. So try doing this with varying the parameters of epsilon and mean points and see how it changes. Try changing the number of sample points, try adding more noise points, try to use some different data set, and try to play with it, and you will get more clarity over how DBSCAN actually works. So that's all for this. Thanks for watching.